Hello. How you guys doing? Funky Friday. Hello Pika, hello Antonio. Formula Z0. Hello H1. Do you guys know what this music is from? Hello Nukas. Will we be trying out our controllers if we have the difference equations ready today? Most likely not. Actually, I mean, yeah, we're gonna save it. We're gonna save it. We're gonna save it for Monday. RuneScape? No, good guess though. Oh, I can call you Zach. Okay. Okay. Hello, Quarone, Berserk, Kate, and Mike. Good morning. Definitely sounds like RuneScape. I know it does. Got my controller done last night. Need to make the difference equation today. Okay, good. For project part 3, to verify the model follows the constraints, we can use the plot only to prove it. Like for example, overshoot. Yeah, you can use the plot to verify that you satisfy the constraints. Yeah, we'll turn this down. We'll turn this down. My report ended up being 9 pages long without code. Okay. This music is from Final Fantasy X, by the way. Cowardly Bean, yes. Hello, V. Adding on to that question, can we draw the settling timelines instead, or would you like calculations as proof? You can certainly throw the settling time lines on your plot to demonstrate that it satisfies the settling time constraint. Just double checking, should our control signal for the ramp also be a ramp? Yes, it'll basically be a ramp. I'm so scared that you're going to say I did something wrong. I'm wrapping up my report and I don't want to change it. Wait, for part 3 we don't have to calculate the responses? Wait, let me look at part 3 really quick so I know what you're talking about. Where are you? Oh yeah, you definitely have to plot. Oh, sorry, Weiss. Well, I mean, even if you've already submitted your project, you can submit an updated version. So, like, if you feel like you need to change something. Okay, for today, the point is, I want to review some Project 1 stuff, and if you have questions, I want to help answer those questions. And in the chat, like, I know a lot of you are already well on your way to being done. So if you want to share some help with the rest of the class, that is always encouraged, as Kate is showing right now. So I think during office hours yesterday, I was advising quite a few people to go back and try doing an iteration of the controller by hand. And I want to show you today what I mean by that with like a little example, because I think if you're stuck trying to adjust the code and you're like, I don't know what's going wrong here, it's often a good strategy to step away from the code for a minute, write out some equations by hand, and then make sure that your code is doing what it should be. Okay. Dr. E, does the report and calculations have to be typed, or is handwritten okay? Handwritten is definitely okay. Just make sure it's neat, easy to follow, legible, and so on. Okay. Let's draw the feedback loop. You got this. You have your output, Y. This is your control input, U, that comes out of the controller. And what goes into the controller is the error. What exactly are you looking for in this report? What I ask for in the description? It's the most direct way to answer that. It's basically a homework assignment. And what do I want? In the project deliverables, it tells you. But like project deliverable 2 says, like, what is the deliverable? Your step-by-step controller process. Detail the steps of how you did your polls, how you designed your controller. So like, it's just like a longer homework assignment where basically I want you to show every step that you did in the process. And you have to do every step anyways. So I'm just asking you to write it down. Okay. All right. Okay, then you have your reference. This is our, for the motor, this is our desired angular velocity. The output is the measured angular velocity. And we're feeding this back and comparing the desired to the measured. So we add the desired, which is the reference, you subtract the measured, and out comes the error. Okay, I want to make up something here. So in the project, we have a first order transfer function. And I'm going to make one up right here. It's going to be something like similar. It's not going to be the same. So it's first order. And then I'm giving you a form for the controller. I want a gain times a 0. And it has 2 poles. These should be minus signs down here. Now, the goal of this controller is to make it so that the poles of your closed loop transfer function, which if we write it like this is like the long form. Poles of this are equal to z star. I used an interpolator function I made to get the rise time. Do I need to show the function in my report? Yeah, just explain it. Just explain it. When I say show every step, can we also just refer to the code that we created? Yeah, explain your code. Is a graphical estimation of the rise time okay? Sure. Okay. The way that this is going to be satisfied, this is the point of the root locus, is you have to verify that the angle criterion is satisfied, that the angle of G times D evaluated at Z star is plus or minus pi, and the magnitude criterion, which is if you take that open loop transfer function, which is G times D, evaluated at Z star, take the magnitude, it's equal to 1. And I think where many of you are getting tripped up is with this angle criterion. All right. So let's talk about that really quick. So I think it's helpful to see this by hand. So this angle is the same as the angle of G by itself plus the angle of D by itself. And this has to be plus or minus pi. So that means the angle of D has to be plus or minus pi minus the angle of G. It keeps giving you numbers over 180. Okay, when you're doing the angle criterion. Okay, sure. So now at this point, what I would do is the angle of D, let's just substitute this in here. It's the angle of this gain, Z minus Z1, Z minus P1, Z minus P2. So I'm going to break this apart because I want you to see this. Let's expand this left-hand side. This is the same thing as the angle from the gain plus the angle from Z minus Z1 plus the angle from 1 over Z minus P1. Oh, and I should put Z stars for the Z here because these are evaluated at Z equals Z star. And the angle of 1 over Z star minus P2. So this is equal to plus or minus pi minus the angle of G of Z. All right, now the angle of just a gain is 0. Antonio says for the KP and KV, can I calculate those with the limit definition in MATLAB instead of pulling them from the graph? I want you to estimate them from the graph. You can always compare it to formulas that we used in class. But I want you to look at your plot. And I mean, you can do both. It's like a sanity check. The number that you get for KV using a formula should be very close to the number that you get for KV pulling it off a plot. Okay? Okay. So at this point, Wait, we can do that graphically? Yes, you can. You can. We can talk more about that later. The trick of this design problem is you're trying to pick the locations of all of these. One of these variables you already know, and I think most of you know this, the cat's out of the bag, because one of our constraints for the problem is that Kp equals infinity, all right? This means that your steady state error for a step reference is going to be 0. You're going to have 0 tracking error for a step. The only way that you can have this is you need an open loop poll at z equals 1. All right, an open loop poll just means that either you have a poll from G that's equal to 1, or you have a poll from D that's equal to 1. Well, in our case, we already know G, and this is a different G, I just made this for example. It doesn't have an open loop poll at 1. So that means that D needs an open loop poll at 1. So then you already know that, it doesn't matter which one you pick, but one of these polls needs to be at 1. And I think we all know that at this point. Okay. So I don't feel bad sharing that with you. So let's say that I set P2 equal to 1. Because I know one of them has to be that, so I'll just do that. So then, really, let's just clean this up a little bit. I know that the angle contribution from the remaining 0 and the remaining pole is going to be plus or minus pi minus the angle of G minus the angle from that pole. And this is where I would take a pause, and I wouldn't go immediately to code. I would check this out by hand. So how about let's talk about this right-hand side, okay? I'm gonna do this just graphically as quick as I can. And I'm going to make up a Z star just for the sake of this. I'm going to say it's, so this is going to be like my hypothetical desired pole, and I'm just drawing the positive conjugate. So if this is 0.4, 5, 6, 7, 8, 9, 10. So I'm going to do this in green. I'm going to have an open loop pole from P2. So P2 is equal to 1. And then for I have to look at G here. I'm going to put that on here as well. So this is just for my example. This is not what you have. So G has an open loop pole at 0.8. And maybe I'll do like a light blue for that. So this is where Z equals 0.8. So what I'm going to do is I'm going to get the angle contribution from G, which I should have done in this blue color, and then I'm going to get the angle contribution for this pole in green. So the way you can do that graphically, let's start with G. You draw a ray from this pole through the desired pole, and you calculate this angle with respect to the positive real axis. And so what I'd like to do is first I find out the angle that's in here, because this is easy to figure out with trigonometry. Like, this is height 0.4, this is height 0.4, so hey, this is 45 degrees in here, so that means the outer angle has to be 135 degrees. Okay, be careful here. So I want to write this over to the side. Like when you're doing the graphical method, the angle of g of z is the angle of, I forgot what I wrote up here. Okay, 0.8 over z minus 0.8. 0.8 over z minus 0.8. So this is the angle of 0.8 plus the angle of 1 over z minus 0.8. The angle of a real number is 0. So I was getting the angle here of this. So this made 135 degrees, right? But because it's a pole, this should be minus 135 degrees. Whenever you're using this graphical method and you find the angle of a pole, it should be minus 135. And actually, how about we jump over to MATLAB really quick? Let's go over here. Because I want to show you over here, you can do the angle here as well. So let's make up G. Let's do, so I'm going to make a transfer function here, because here's another way you can do the angle. So I have numerator, denominator, and sampling period. I can't even remember what our sampling period is. I guess it doesn't matter, I'm just doing an example. It's 20 hertz in the report. So the sampling period is 1 divided by that. And so I have 0.8 divided by z minus 0.8, right? Okay. And then in my case, z star is 0.4 plus 0.4i. So what I can do is I can evaluate g at z star and take the angle. And this should give me the angle in radians, which should be 135 degrees, but it's going to be minus 135. So like, this is 2.3562. So if I convert this to degrees, you multiply by 180 over pi, and it's minus 135. Okay, so let's go back over here. So it's minus 135 degrees, but up here you have minus g of z. So I have minus of a negative number. Because remember, this was minus g evaluated at z star. So just remember that this part is equal to minus 135. Actually, we should put it in radians here. Minus 2.3562, but you're going to subtract that, so you're actually going to be adding a number there. That's probably something you might have run into. Okay, let's move on. Let's do this pole. So this is the contribution from this pole. So just like I did for G, I need the angle out here. So first we do this interior angle, then we'll figure it out. So it'll be the tangent of that interior angle, like I'll call it just green theta. It's going to be 0.4 over 0.6. So theta is the inverse tangent of 2/3. What is that? I'll do this. 33.6 33.69 degrees. Okay, that angle in there, 33.69 degrees. So the angle out here is 180 minus 33.69. I'm going to plug that into MATLAB real quick. So it's 146. 146.31 degrees. Okay, so now. And remember, this is going to be the same thing as what we had with G, because we're subtracting a negative number. Let's convert 146 to radians. So I have to multiply that by pi divided by 180. So this is minus 2.5536 radians. All right, so now we're going to have, so I'm going to rewrite this equation. The angle of z star minus z1 plus the angle from that pole is going to be plus or minus pi plus 2.3562 plus 2.5536. And if you do the plus or the minus pi, you'll kind of get a different answer here. But I mean, you'll get the same angle. So plus 2.3562 plus 2.5536. Let's also do the minus pi version of that. Wait. Did I do that right? Yeah, I guess that's right. Because look, these are the same angle because they're just 2 pi different from each other. And if you go 2 pi around, you come back to the same angle. Like if I take this and I subtract 2 times pi, I get the other angle. So really, this is all the same angle. Why are those angles positive? Because of what I've just been doing. Everything leading up to this has been, why are these angles positive? Like this. Because I calculated these angles here, they are positive angles graphically, but a pole contributes a negative angle using this graphical method. So if I find this angle out here, sure, I got 146 degrees, but because it was from a pole, it's negative. So that's why up here in the original equation, I'm subtracting the angle contribution of the pole. The angle contribution of the pole is negative, but because I'm subtracting a negative, it becomes a positive. So that's why I had plus. So I'm just going to put this is equal to 1.68 or 7682 radians because the other number that I got that was larger, it's the same angle. This is just a smaller number. And if I convert this, to degrees, just for giggles, or 101.3 degrees. Okay, so now, the question is, so this is the control design question. Where do I place the 0 of this controller and where do I place the pole so that the net angle is 101.3 degrees? Now the way that I like to do this, and this is not the only way, but this is how we've done it in class, is first you have to recognize there's infinitely many combinations of these that can give you this angle. So you're just going to have to pick something to start. Now, even though there's infinitely many combinations, that doesn't mean you can just give any angle for the zero. There's a minimum angle that you can achieve, and there's also a maximum angle. So, to help you understand this, negative kV is impossible. It's not impossible. We can talk about that. And it's not a big deal if it's a negative number necessarily. Okay. So this pole always contributes a negative angle. That's just what poles do. So that means that the smallest angle I can choose, the zero, in this case, is 101.3 degrees. The reason this is the smallest angle that I can choose for the zero is because I need the combination of these angles to be 101.3, right? And the pole only gives a negative angle. So let's say, like, if I pick 50 degrees, well, I still need to go 51 more degrees to get to 101, but the pole only contributes a negative angle. So the pole isn't going to ever make it more positive. So the smallest angle the zero can make is this positive angle on the right-hand side. All right? And then the other thing is the largest angle is 180 degrees. And really, we'll never even get to this point because this, if you look at it geometrically, this would require z1 equals positive infinity. And we generally don't like to go there. Okay, but the point is, you find the smallest angle that the zero could contribute, you find the largest, and then you just have to pick some angle in that range. So, and this is what the code helps you do, because you can iterate through many possibilities. But first, I would just do one by hand. So what I'm going to do is I'm going to pick 150 degrees. I have no intuition about that angle. I have, if this is going to make a good controller or a bad controller, it's just, we're going to try this. So if I know that I want this zero to contribute 150 degrees, what I have to do is go back up here. And actually, I can use this as a guide. Like, this pole was at 0.8 and it made 135. This one was at 146. It was at 1 and it made 146. So I have to actually have a pole that's outside the unit circle. So maybe I'll pick one, like, I'm not sure it'll be exactly here. We'll solve for it in a second. But I'm just kind of roughly drawing a location of a zero that gives 150. So I know this will be 150 degrees. This is z equals z1. And I don't even know what z1 is yet. Hello, not prof. It's been a little while. Welcome back. Okay, so that means this interior angle has to be 30. Okay. And so what I'm going to do, I know like this side is 0.4, and how far does this have to be? I'll call this distance like x. So the tangent of 0.4 over x is equal to 30 degrees. So that means 0.4 over x is the inverse tangent of 30 degrees. So that means x. Wait, did I do this right? Well, wait, no, 0.4 over x is the tangent of 30. I'm a goober. Okay, so then x is 0.4 over tangent of 30 degrees. Let's plug that in there. Arctan 30 degrees is weird. Yeah. Okay, what's 0.4 tan d? Should we show by hand calculations in general is a good question, like for the selection of z star and the angle calculation. You don't have to do this geometric way that I'm doing right now. The reason I'm showing this is I think it's good to go back to these fundamentals if you're getting stuck in the code, because the whole way that we derive that code is automating what we did by hand. So I think it's good to come back here. Wait, why is it 30 degrees and not 150 degrees? Okay, what I'm trying to do. Okay, this is 0.6928, by the way. No, you're right. I'm trying to place the 0 so that it makes 150 degrees relative to our z star, but I don't know the location exactly on the real axis where it should be. So that's why I'm solving this trig problem for this distance x in here. So this means z1, because at this point of the pink triangle, z is equal to 0.4 here. So z1 is 0.4 plus this distance x, because that brings it over to this point z1. So x, so that's 0.4 plus 0.6928, which is kind of sad I can't do this in my head. 0.6928. Okay, so it's 1.0928. Doesn't the 150 degree make it non-minimum phase? It could. But I'm just showing in it an example right now that some of these controllers that you might come up with are, you may find that it doesn't place the closed loop poles in a totally desirable place. Okay, but don't worry about that yet. Okay, so 1.0928. So we put that there. Okay, so we know that the combination of the 0 and the pole has to make this angle, and I arbitrarily picked 150 degrees for this, and we found that z1 has to be at 1.0928 to do that. And then, so if I picked 150 degrees for the 0, overall I need 101.3 degrees. So the pole needs to be 101.3 minus 150 degrees. So that overall it adds up to 101.3. So 101.3 minus 150, I need minus 48.7 degrees for the pole. So if you're doing this graphically, at this point, you go back up to your plot, and I say, okay, where can I place the pole so that it makes 48 degrees? And I know this is getting really cluttered at this point, but I think you get the idea. I'm going to draw something that looks, I don't know, maybe this is 48 degrees. So it's going to be close to 0. Z equals P1. And you can do the same thing here. I have to figure out, like, this point is Z equals 0.4, and then I just have to shift over until it makes 48 degrees, and that's going to tell me where my pole is. Okay, we're so close, maybe we should just finish it. So the tangent of 48 degrees is equal to 0.4, and then instead of using X, I'm going to use W. You didn't see that coming. So this distance here is W. So W is 0.4 over tangent of 48 degrees. Zero 0.4 divided by tangent of 48 degrees, 0.3602. So this distance in here is 0.3602. So that means that the location of my pole is 0.4 minus 0.3602. Let's get it. 0.0398. So it's pretty close to 0 here. Okay, let's put this here. 0.0398. Okay, now, let's just put our controller together. I want to show you this. So d of z is a gain times z minus z1, which is 1.0928. And then I'm going to have z minus my pole, 0.0398. And then I had z minus 1 as one of these. And I don't have the gain yet. So you have to find the gain such that the magnitude criterion is satisfied. All right, let's go over here. D with no K yet, or donk. I'll just call it D no K for now, just to avoid any confusion. I'm going to make the transfer function numerator, denominator, sampling period, which is 1 divided by 20, aka donk. Okay, so we're going to have we're going to have z minus 1.0928, and then actually the quickest way to do this is to make a polynomial with roots at 0.0398, where one of my poles is, and the other pole is at 1. So this is D with no K. This is the transfer function that we made. So K is going to be, well, let's start with this. I take G times D, no K. I'm going to evaluate that at Z star. I'm going to take the magnitude of that using the abs function, and then I'm going to do 1 divided by that. So this formula we've talked about in class before. So K is 0.3431. So if I go back over here, this is 0.3431. So now I can say D is K times D with no K. Okay, now that I've made this controller, the one and only Donkosaurus Rex, exactly. Here's how I check if my work is done correctly. Now, I just did this today for the first time in front of you guys. I mean, this particular problem. This isn't my first time doing a problem like this in general, but I could have messed up. So how do I know if this is correct or not? So here petition to call us Donkers. Hello, Donkers. Okay, eval. So let's check if I satisfy the angle criterion. So I take the open loop transfer function, I evaluate it at Z star, and I take the angle. Remember, if I did my work right, this should be equal to plus or minus pi. So it's equal to almost minus pi. So this level of error, this will happen if you're doing it by hand and you're truncating decimals like I did. You're going to be able to get this much closer if you do all of your operations in MATLAB. Okay, so, but looking at this, I know that I'm pretty close. I think I generally did this right. And then let's check the magnitude criterion. So instead of taking the angle, I take the magnitude of this. The magnitude should be equal to 1. Okay, and it is. So as long as the angles add up to pi and the magnitude is 1, we should be fine. You're not entirely fine yet. Let me tell you why. Okay, your next step. This just lets you know, hey, you designed this controller correctly. What you have to check is your closed loop poles. Because if you satisfy the angle and magnitude criterion, that means that 2 of your closed loop poles are going to be at Z star. So let's check that first. But the third closed loop pole could be unstable, or it could be in a terrible place. So let us. Okay, the quickest way to make your closed loop transfer function is to use the feedback command. And then you put your open loop transfer function here, and then you put a 1 here, and this gives you your closed loop transfer function. Look, it's third order. It has 3 roots. It's going to have 3 closed loop poles. So what you can do to get your closed loop poles, you use the pole command on G closed loop, and look, ooh, Z star. Okay, here's the thing. 2 of my poles, these ones, are very close to Z star. I wanted 0.4, 0.4, right? It gave me 0.39 and 0.3999999. So it's very close, and the reason it's not exact is because of truncation errors. All right? But what about this? Is this good or is it bad? Yikes, we have an unstable pole. Yes. The third closed loop pole is outside of the unit circle, meaning this system is unstable. So it's bad. So what I need to do at this, you need to run. No, what you need to do at this point is you have to go back to the beginning and you have to go to where you made this assumption, picking 150 degrees. And you have to pick something else. Discord until it makes sense. This is bad. Very, very, very bad. You have to pick something else. Now, this is why it's good to build a code, because all of this stuff that I did by hand just now, if you know how to do this by hand, you should be able to write a code step by step that does each of those things. And in your code, what we did, because we built a code together in class, and we made it check a bunch of controllers between the smallest and largest angles. And you could try 10 controllers, you could try 100 controllers, 1,000 controllers. It doesn't matter because it's a computer doing it for you. But the computer's going to do the same thing that I just did. And then what you should do is, afterwards, you look at all those controllers and you look at their closed loop poles, and you find a version of the controller that looks beautiful and doesn't have an unstable pole and doesn't have a pole on the negative real axis, those kinds of things. Okay, I know. So I wanted to run through that because if you're somebody who's been like really stuck, what I just did is like what you need to do. And I know I've ignored like a lot of questions that came up in the chat. So you can throw those up in the chat again if they haven't been answered yet. Oh shoot, but I gotta run to another class in like very soon. So it has to be quick. The closer the pole is to 0, the more dominant it is. Question time. No, the farther a pole is, oh, never mind. The farther a pole is from the origin, the slower it is. You call the slowest pole in your system is called the dominant pole. You want your dominant poles to be Z star. So you don't want any closed loop poles to be farther than the origin from Z star. All right. We wouldn't need to change Z star as long as they are within the satisfied region, right? That's true. Like, you should be able to pick a Z star and not have to iterate on that again. You could, if you want, to just try a different controller, but if you pick any Z star within the constraint region that works, you should be able to find a controller that satisfies the constraints. Oh yeah, how do we graphically find Kv? Okay, what you need to know, the definition of Kv. So if you provide a unit ramp reference to your system, then the error as k goes to infinity of Vk is equal to 1 over Kv. So let's look at this. A unit ramp looks like this. It has a slope of like 1 as a function of time. And your controller is going to probably do something like this. And so once it reaches its settling time, it's going to maintain the same distance between the reference the whole time, like until infinity. If you go on to infinity, it's still going to like look exactly like this. So what you do is you simulate up until you get to the steady state point, and then you calculate what is this gap in here. So this is the error. And this is going to be, because this isn't at infinity, it can't be exactly equal. But because you pick this I don't know, maybe 5 seconds into your response. This is approximately equal to 1 over kV. That's it. So somebody asked, like, is it possible to have a negative kV? Yes. You have a negative kV if your response does something like this. And you're actually like on top of it. So that's not necessarily bad. It just means you're overshooting the reference a little bit. So you could have a negative kV. If you're doing Kp, you can do the same thing with the graph. We're having a step reference. Actually, our reference is... So the reference looks like this, but we're doing an amplitude of 2 pi. So it's not a unit step. And your signal... I don't know, I'm just going to make something up. Maybe yours does something like this, but it's going to be like really, really close. So maybe if you like zoom in MATLAB, you'll find that they're like a little bit different. And maybe it's like 10 to the minus 4. Maybe it's smaller than that or something. But Kp, let's see, for a unit step reference, the error as we go towards infinity is 1 over 1 plus Kp. I think if it's 2 pi, then this is actually 2 pi. I'm pretty sure. But Kp for you guys is going to be it's going to be such a huge number anyways. Like this 2 pi really won't make a difference. You're going to get like just a humongous like 10 to the 14th, or I don't even know. Should we be worried if the control signal for our ramp response is linear? No, that's fine. I really want to know if my controller works, or is it time to give up on becoming a controls engineer? No, even if it doesn't work perfectly, whenever you're doing a control system, remember, we're using a model that is, I think it's a pretty good model. So I think your control system, if it works in simulation, it should work in real life. But that's never guaranteed when you take a controller and put it on a real piece of hardware, because the model is an abstraction of a real life thing, so it won't totally work. So is it okay that Kp is found to be infinity because error is actually 0? Sure, but I'm saying if you look at the graph, I don't know if you'll find it to be exactly, I don't know if you'll find the error to be exactly 0 from a graph. The point of looking at a graph and doing these is it's supposed to emulate running this on hardware and just verifying that everything's working. The vertical difference is 0.25. Did you do something wrong? Maybe? Yeah, I would check your well, if you have an open loop pole at z equals 1, the error should be much smaller than that, I think. Yeah, it should converge to 0. T. Jackson says, thanks, has been very helpful. I'm so glad. Yeah, I wanted to make this very helpful for you guys. My Kp is like 2 pi divided by that. Is that okay? Yeah, I think that should be fine. I think that should be fine. I meant to say Kv. Oh, your Kv. Oh, that seems pretty good. If you have an error like that, yeah. Also, I'm going to upload a Google Doc where you can upload your controller parameters, and that'll be an easier way for me to pull them out and test them when we come to Monday. Hey, Quaron, glad this was helpful. Thank you, Kate. Have a great weekend, everybody. Have a great weekend, Pika. It's always great hanging out with you guys. I would hang out longer in chat, but I got to go to the next class. I'll see you guys soon. Happy Friday. Happy Friday to you guys. You guys are doing great. Keep it up. You guys are doing fantastic. Hang in there. Can we come hang out in the next class too? Oh yeah, you can just come to the next class. It starts at 1:50. So you're welcome to hang around. But I'm going to reboot this in about 10 minutes. All right, peace everybody. Enjoy your weekend. See you.